Hello and welcome. Today we're going to look at rolling without slipping, and as a side note, we're going to look at rotational kinetic energy and solving problems using conservation of energy with things that are rolling. So here we have a, let's say, wheel that's rolling on the ground, and it's rolling with an angular velocity of omega. So if it's rolling with an angular velocity of omega in that direction, that means that the center of mass of this wheel has a translational velocity. That is going to this direction, the velocity of the center of mass. And we can relate omega to the velocity of the center of mass with r. So let's say that this wheel has a radius of r. So if this object is rolling without slipping, then from the wormhole equation, we know that the velocity of a point on the rim of this wheel is going to be going that direction as well. And it's going to be related with velocity of that point is equal to r times omega. And if this is rolling without slipping, then we can say that the velocity of the center of mass, as a matter of fact, is equal to r omega. So this is the condition for rolling without slipping. The velocity of the center of mass is equal to r omega. So this would be like a bike tire going down the road, a car tire going down the road if it's not slipping on the ground. If the velocity of the center of mass, and I don't know why my screen is doing this, if the velocity of the center of mass is not equal to r omega, I should probably use the same r that I used in my wheel. So if the velocity of the center of mass is not equal to r omega, then this is going to be rolling with slipping. And we're not going to look at those today, but at a future date. All right, so for everything that we deal with rolling without slipping, anytime the textbook tells you rolling without slipping, then you know that this condition holds. The velocity of center of mass is equal to r omega. All right, now what that leads to is some interesting effects in terms of energy. This wheel is traveling from left to right, so it has a translational velocity. So we can talk about the translational kinetic energy of the wheel. And we've already used translational kinetic energy. It's 1/2 mv squared. But the wheel is also rolling. And so it's got little discrete pieces of mass, and those little discrete pieces of mass all have a velocity that is equated by the angular velocity and r. So each of those little discrete pieces of mass also has a kinetic energy. So when this wheel is rolling, it's got a translational kinetic energy and it's got a rotational kinetic energy. So let's clean that back up again. And again, we've got some omega this way. We've got then a velocity of the center of mass of the wheel this way. We've got a radius of r. And then let's also give our wheel a mass m. Let's say this is a solid disk moving to the right. So maybe a car wheel could be approximated as a solid disk moving to the right. So we talked about it's got two kinds of kinetic energy. It has translational, and this is the kind of kinetic energy we've already dealt with. That's 1/2 the mass of the wheel times its velocity of the center of mass squared. But it also has rotational kinetic energy. And as we've seen already with all of our rotational equations versus the equations that we use in the linear world, then the rotational kinetic energy is analogous to the translational kinetic energy. And we just have to use the rotational analogs of our variables. So it's going to be half of the rotational version of mass. Remember, that is the rotational inertia. And it's going to be times the rotational, or the angular velocity squared. So the rotational kinetic energy of this disk can be given with this equation. So then the total kinetic energy is given by the translational, 1/2 mv squared, and this is velocity again of the center of mass, plus 1/2 I omega squared. And remember that I is going to depend on what object is doing the rotating. If it's a solid cylinder, if it's a disk, if it's a hollow cylinder, if it's a solid sphere, if it's a hollow sphere. All those guys have different rotational inertias. And that omega is also related to the velocity of the center of mass. We can say that VCM is equal to R omega. So then omega is VCM over R. And we can use that to solve for problems. So let's do a couple examples. All right, for this example, we are going to look back at the inclined plane, the famous inclined plane. We're going to ask which rolls down faster. It's a little game. So let's say that we have a solid sphere of mass m and a radius r. And we're going to start it from rest down the ramp. And we want to know how fast is it going to be moving at the bottom of the ramp, V final. And to remind ourselves, a solid sphere, the I for a solid sphere is equal to, given out of the textbook, 2/5 mr squared. And let's compare that to a solid cylinder. We're going to roll that guy down, and we're going to say he also has a mass m and a radius r, same mass, same radius, and according to the textbook, the I for the solid cylinder is 1/2 mr squared. So who's going to be going faster when we get down to the bottom of the ramp? All right, and so we're going to say that both of these guys start from a height h, and they're both going down the same ramp. We don't really care what the angle of inclination of the ramp is. All we have to care about is h, because we're going to use conservation of energy to solve this problem. So if we call this point 1 and this point 2 down here, we can say that the gravitational potential energy at point 1 is going to equal the total kinetic energy at point 2. And this is where we have rolling without slipping. We have to take into account the translational kinetic energy and the rotational kinetic energy at the bottom of the ramp. So at the top of the ramp, we've just got our classic mgh. And at the bottom of the ramp, we have the translational kinetic energy, 1/2 m v final squared, plus the rotational kinetic energy, which is 1/2 I omega squared. And we have to remember that with rolling without slipping, then omega is equal to VCM over R. And that's going to be true for both the cylinder and the sphere. The only difference is going to be I. The I is different for both of them. And we also need to be clear here that V final and VCM are the same thing. So we need to write those more consistently. Let's go ahead and just write them both as VCM. So VCM squared, the velocity of the center of mass at the bottom squared, and then over on the right-hand side, we're going to have the velocity of the center of mass divided by R. So let's first do the sphere. So it's the mass of the sphere, mgh, on the left-hand side, and we have 1/2 mass of the sphere, velocity of the center of mass squared, plus 1/2, and again, I for the sphere. I need to go back up and look. It is 2/5 mr squared times omega squared, but that's velocity of the center of mass, over the radius, that whole thing squared. So we have some canceling that we can do here. We see that we have an m in every term on both sides of the equation, so the mass of the sphere cancels out. And if we look over here on the right-hand side, we have r squared on top, and we're going to end up with an r squared on the bottom, so that cancels out as well. So doing some simplification, we've got gh is equal to 1/2 of VCM squared plus, do some canceling here, the 2's go away, we've got 1/5 VCM squared. So, more simplification. GH is equal to half plus a fifth. Let's see, we've got 5/10 plus 2/10 will give us 7/10 VCM squared. So solving for VCM, we've got 10 over 7 times GH, and we're going to take the square root of that. And that's going to get rid of all of that. So this is for the sphere, 10/7, square root of 10/7 GH, and that's the velocity of the sphere. So now let's do the cylinder. It's the same equation. The only difference is that term right there. Instead of 2/5 mr squared, it's going to be 1/2 mr squared. So let's set it up for the cylinder. We have mass of the cylinder times g times h is equal to half the mass of the cylinder, VCM squared, plus half of I of the cylinder, which is 1/2 mr squared, times omega squared, which again is VCM over r squared. So the same types of simplifications happen. Mass gets canceled out in every term. This r squared goes away, as does this r squared. So we end up with GH is equal to half VCM squared plus, this time it's 1/4 VCM squared. So more simplification, GH is equal to half plus, let's see, 2/4 plus 1/4 is 3/4 VCM squared. And solving, we have 4GH over 3. Take the square root is equal to VCM for the cylinder. And going back to the last page and writing down what we got for the sphere, it was 7/10 or 10/7. So let's write that down. 10GH over 7 square root is equal to VCM for the sphere. All right, so who made it down faster? We need to compare those fractions, 4/3 to 10/7. 4/3 we can write as a decimal approximation, 1.33. We divide 10 by 7, we get a decimal approximation of 1.43. So the velocity on the right is bigger than the velocity on the left. So our winner is the sphere, getting to the bottom of the ramp first. All right, so we can use conservation of energy with these rolling without slipping problems. Just make sure you remember to use the translational kinetic energy plus the rotational kinetic energy. Okay, so our second example deals with an Atwood machine, and we have done these before, but every single one of them had a massless pulley. This time, our pulley is massive, which means that as this system accelerates, the pulley itself is going to accelerate. All right, so the question that we want to ask is, if these guys, M1 and M2, both start at the same height off the ground, what is the velocity of M2 going to be right before it hits the ground? That final velocity right there when it falls that distance h. Okay, so we're going to define a, well, we don't need to define a common positive direction because we're going to use energy to solve this. If we look at this system right here, then the system has gravitational potential energy before we release it, and that gravitational potential energy is going to be converted into kinetic energy. So if we call this situation point 1, and when M2 is about to hit the ground, we'll call that point 2. And we're going to compare the energies at point 1 to point 2. So the system is not moving, so we can say that the gravitational potential at point 1 is going to equal the gravitational potential at point 2 plus the kinetic energy total at point 2. And we're going to have three things with kinetic energy. M1 is going to be moving upwards, M2 is going to be moving downwards, and the pulley wheel itself is going to be rotating, so it will have rotational kinetic energy. And M1 is going to go higher, so his gravitational potential is going to increase, M2 is going to go lower, his gravitational potential is going to decrease, and we'll call this point at the ground our 0 point of gravitational potential. And just briefly, we don't need to consider the gravitational potential of the pulley because it's not changing at all. It's fixed in place. I could have it on both sides of the equation, but it's just going to subtract out. So since the gravitational potential of the pulley is not changing, we're going to ignore it and just deal with the changing masses. So the gravitational potential of the system at point 1 is going to be m1gh plus m2gh. And we're going to set that equal to the gravitational potential of the system at point 2. m2 goes down to 0, m1 goes up. So it's going to be m1, the only thing with gravitational potential, and it's gone up a distance now 2h above the ground. And now we're going to add in the total kinetic energy. We've got m1 with kinetic energy. We've got m2 with kinetic energy. And we've got the pulley wheel, which is going to be 1/2 I omega squared. So I'm obviously going to need to write this in a place where I have more room. But there is our setup. So let's give ourselves some more room. Okay, so here we are. Big, long, seemingly ugly equation, but some really nice simplification happens, and we're going to be able to combine a lot. What we need to understand here is, first off, this velocity and this velocity are going to be the same. Block M2 is going to be moving down with the same velocity as block M1 is moving up. And we also need to recognize that omega, since this is rolling without slipping, the string's not slipping on the Atwood machine, is going to be equal to the velocity of the system divided by the radius of the pulley wheel, v over r. And that velocity v is the same as this one, which is the same as this one. The other thing to recognize is we're going to assume that this pulley wheel is a disk. So I for the pulley wheel is given by the textbook as I for a disk or a cylinder, and that's going to be 1/2 times m r squared. So we're going to plug that in for I. We're going to plug in v over r for omega, and we're going to do some combining. All right, so over here on the left side, we can pull out a gh, and that's going to leave us with gh times m1 plus m2. Then moving over here to the right-hand side, I've got an m1, let's put a 2 out front, m1gh, plus, now we've got the same v in both this term and this term, and we've got a 1/2, so let's pull that out front, 1/2 of v squared, and again m1 plus m2. And then adding on the last term, we're going to plug in our I, that's 1/2 mr squared, and then we're going to plug in our omega, v over r, that whole thing squared. So now let's take a look at some simplification that we can do. Again, this r squared is going to cancel with this r in there, and we're going to multiply these two halves together to get a 4th. So, and then let's move this guy over to the other side. So we've got gh times m1 plus m2 minus 2 m1gh is equal to 1/2 v squared times m1 plus m2 plus 1/4 mv squared. All right, so here we are. I probably should not have pulled the gh out over here because I've got gh times m1. So that's m1gh minus 2 m1gh. So that's going to give us a negative m1gh on the left side. So we've got m2gh minus m1gh. And then over here, again, I've got a 1/2 v squared and a 4th mv squared. And we're going to want to factor out that v squared. So let's go ahead and do that because there's a v squared in both of them. So that's going to give us 1/2 of m1 plus m2. And then it's going to give us plus a 4th of big M. And there is our v all by itself. So now we just need to finish it off. We've got m2gh minus m1gh all divided by 1/2 of m1 plus 1/2 of m2 plus a 4th of m. And we take the square root of that whole thing, and we get the velocity at the bottom. And you might think, wow, that sucked. And it was intense algebra, but it was not difficult algebra. And believe it or not, doing it that way is a whole lot easier than using forces and torques and solving for the acceleration of the system and then using a kinematic equation to find out what the final velocity was at the bottom. So there it is. We're going to do a problem set next time in class. I'll see you then.